Hello, everyone. I'm Sadhya Loganathan, and I'm here to present to you the project that I've been working on for this semester as a part of the CS 715 Pro course. And that project is about generative image augmentation for store layouts using Domain Gap Embeddings framework. So this is based off the Domain Gap Embeddings generative dataset augmentation paper. So before we begin, I would like to acknowledge the some people that was responsible, who contributed to the completion of this research. So initially, I would like to thank the authors of the DoGE framework, which is what I used as part of this project. And I would also like to thank my instructor, Professor Jingtao Yao, for his guidance on this project. And I would also like to thank my batchmate, Kapish Kaul, for providing some GPU resources which I was used as a part of this project. So before we begin, I'll introduce you what the overview of the whole project is going to look like. So initially, I will walk you through the introduction of the project and the objectives behind it, and then why the DoGE framework was used here, and the proposed work and the methodology that is behind the research and the outcomes of it, which is in the form of an experimental setup, results and analysis, and the limitations. And finally, the conclusion of this research. Introduction. So the reason the project is based on being able to, so the problem that we notice is that in store layouts, at least as a part of a previous project that I worked on again for UFR, there's a project that I was trying to work on optimizing store navigations for store layouts. Basically, in retail stores, we would need to optimize the navigations and operations within the retail stores. And as a part of that project, it was also necessary to analyze the store layouts and be able to navigate how to optimally navigate through them. So for that, a segmentation task on those store layouts was a part of the process. And one of the problems that I faced was limited datasets available on these store layouts. And I needed a diverse set of datasets so that I can test out different algorithms and different store layouts for that project. And that is a problem that I noticed, and I wanted to experiment in the future using GANs. And for this project, I was basically experimenting on how we can use generative adversarial networks and the concepts behind and the logical flows behind it to be able to use that to generate the images for store layouts. So this is basically to optimize the store customer flow and the operation efficiencies of store layouts. So basically, it could include Walmart, superstores, and any retail stores. And the problem is that the limited availability of the datasets of those layouts. So usually these companies would keep their blueprints or store layouts private. And the purpose is to be able to generate datasets of limited datasets so that we can then use that for the optimization task and train the different models that we might have. The problem dataset, again, is what I just now told, is the inadequate datasets for the training. And hence, I go forward with this framework. And also, the other problem is that the layouts also, the generic layouts that are not specific to retail stores lack the specific features that are required for layouts, retail stores. At least the aisle formations and whatnot is limited for the retail stores, which in cases like blueprints about houses would include boundaries that are different from what you might see in a retail store. So the objectives of the research is to leverage the DoGE framework, which is basically extracts the domain gap embeddings from specific source targets, and then be able to use that on a limited dataset that we've aggregated to be able to generate good datasets. So like the problem that I explained, where there is a need for more data, you can generate these datasets and then use that for the other training tasks. So here, what I basically experiment on is seeing is how the DoGE framework can be useful for a diverse dataset that I collected as the source, and then use that on this limited dataset. So the goal is to achieve more diverse data sets on store layouts. And the key objectives that I do as a part of this project is to collect datasets for the source and the target. So I'll explain what the source and the targets are in the upcoming slides, and to fine tune the DoGE framework so that they're specifically suitable for the store layout generation, and to conduct experiments and identify ideal configurations that are suitable for generating these store layouts. So why the DoGE framework? So again, the main reason behind the DoGE framework is that the way it is architected, or the solution is architected, is that you will basically collect a source dataset, which is diverse and generic, which is not specific to the dataset that you're trying to generate. And then you learn those features and extract those features from that dataset, and then be able to use those extracted features, which are what we call as domain gap embeddings, and use it on limited datasets. So that's why we refer to as the few shot learning. Basically, if you have a limited dataset that you need to generate more data from, you can use a generic dataset and then extract the embeddings and then be able to generate on that limited datasets. So your distribution will now, the generated dataset would now follow the distribution of this limited target dataset that we have. So that is why the DoGE framework looks specifically useful in this scenario. And also the other advantages that why this could be used is the realistic data generation, because they also have an option to control the generations by using a ControlNet, which is what you can see on the top layer of the architecture, which enables you to experiment with different control structures. It could be a structural control, it could be a segmented control, so it could all this facilitates the different realistic kinds of generation that you can need for the specific problem. The proposed work is to be able to collect the datasets for the source datasets. So for the source dataset that is aggregating a diverse datasets that fit the criteria for the source datasets, then also aggregate a dataset that is fitting the suitable criteria for the target dataset, and also then bridge the gap between these two by experimenting different configurations of the DoGE framework and fine-tuning it based on this dataset, so that the framework can now generate images for store layouts. So the source dataset consists of multiple datasets, which we'll look at in the upcoming slides. But yeah, the proposed work is to be able to aggregate these two datasets, the source and the target, and then fine-tune the DoGE framework to be able to generate store layouts. So the methodology of the research. So the first step of the methodology would be to collect the dataset, which would be the source and the target dataset separately. And then once the dataset is collected, we'll be performing the domain gap extractions on this source dataset to form the domain gap embeddings. And then using this domain gap embeddings, we generate the datasets for the target distribution. So that would be the complete methodology of this project. So the source dataset. For the source dataset, I went through eight different data sources. Again, before this, I had also gone through other different data sources, but due to the limitations of accessibility and due to the limitations of accessibility and the dataset not being public, only some of these were selected. Some of the datasets were selected, and the filtered criteria, the filtered datasets are provided on this slide. So as you can see, the RPlan, SunCG, structured 3D, all these data were available. Unfortunately, the SunCG was discontinued, but the dataset was available, but the author's permissions was discontinued, and they removed the access, except for the other datasets were used here. And also there's a large amount of dataset that is provided from this. So we randomly sample some subset of this for the generation, so for the source dataset. So I would not use the complete dataset, but on each iteration and on each experiment, I would randomly sample from this pool of data for the source data so that it is generic enough and it's good enough for the generations. So this is the base dataset for the source dataset. And some of the data that looks like what it looks like in the source dataset is what you can see below. So I've taken a sample of 10 images here to see how the image, how the blueprints would look like. These are not specific to store layouts. These could be house image, these could be house layouts, they could be university layouts, depending on what the dataset is from. Some of them also contain blueprints of building structure. So they are containing some information about how a building is structured and how a layout is structured, so that these can be useful to structure the outputs, and the DoGE framework can learn from these inputs to be able to generate the outputs that is expected. And for the target dataset, this is a sample of what the target dataset looks like. For this, what I did was I wrote a script, a Python script that can scrape down information from the Google, because there's no public dataset about store layouts. Unfortunately, as these are private information that is kept by these private entities. So on whatever that is publicly available on Google is what I collected as a dataset. I collected 500 images for this, and these 3 sample images are provided here. And we'll go through some of the other sample images that might be there in the dataset, but these are some 3 examples to understand what this generated data should look like. And again, these text would be removed as part of the pre-processing step, so that the text would not be seen in the output generated. And just for the structural understanding, we see how the structure of the layout would look like. So if you do go back to the previous one, you'd see these are more closed rooms, enclosed spaces, but these are more open spaces. So this is what the overall structure of a store layout would look like. So the methodology. Now the next step after the data set is collected, what basically we do is, using different embedding methods, we extract the information from the source data set. So there's 2 different options to choose from. There's a difference of means and there's a principal component analysis. So from these 2 different options, there's different configurations that I go through, 10 different experiments that I did. And from those 10 different experiments, I check out which one different experiments configurations are changed around to identify what actually generates the better outcomes. So we look at that and then generate the embeddings. So the first step is to extract the domain gaps and generate the embeddings, and then using those embeddings and the target datasets, we generate the output for the new target domain. So the experimental setup. So for this setup, for this purpose, it was required to use GPU. So the code that was provided by the DoGE framework was installed. So we set up the environment for for installing this software. So CUDA and PyTorch were necessary to be installed on this GPU environments. And the setup for as also as a part of the DoGE framework, there's a set of libraries that were needed to be installed. So all of these were installed on this environment, and then the configurations that were tested were provided below. So there's 10 different experiments that were conducted, which we'll go through. And those 10 different experiments were tested to see how the output diversifies based on the configurations that DoGE framework has and how the model fine-tunes to generate those different datasets. So now we'll be going into a demo and to see how the generations work and how a sample generation will look like. So as you can see, now we can look at the experiments that we conducted. So on the right, you can see the 10 experiments that I conducted to do this research for the generation of store layouts. And you can see the code for each of these experiments here. So the first one is for the extraction of the domain gap embeddings, and the second one is for the generation. So we can just experiment on extracting the domain embeddings from the source dataset for the target. So you can see the GPU is being heavily in use. Yes, as time progresses by, you'll notice that it spikes to 80%, and that shows that the CLIP model is now extracting the domains and converting those images into embeddings. And those embeddings are what you can see is being created in this EMBD folder. The many folders here, those are the embeddings that we can see. And each of these experiments are different configurations that are provided for the different configurations. That is what is included in the report, and we can see a sample of these images for different experiments that we conduct and what type of description that is provided for these images. So you can see that some of these are realistic but not focused, some of them are good but good generation, some of them are not too clear and distorted, and you can see the different set of images. And you can also see that there's another folder called the grid, which we'll look into. And this is basically how the gridding of this image generation works. So the extracted embeddings will show the grid structure that is available for these generations. And you can see different for a specific same image how the grid would look like and the generation would look like. This is a bad example, at least like this is a bad generation. And we can see the different experiments and how they differently generate datasets. And yeah, I've also added some remarks for this. You can pause and look at that and see what type of image that is being generated. So I'll go through all the 10 experiments briefly, so you can get a brief understanding. And on the top, you will notice the table that provides the configurations. In these configurations, the abbreviations also provided the initial table that is which contain all the 10 experiments. Now that we've seen the demo, we can see that how the generations were analyzed. We saw that how the 10 different outputs were performed. Now we look at the results analysis. So the evaluation criteria for each of these generated images is that now that we have all the images generated, we need to evaluate how realistic the images are and how structurally integral the images are, and are they diverse enough. So these three are the evaluation criteria that we form on the dataset. And then the key findings based on these three criteria is that the best configurations for this the evaluation criteria, the difference of means and canny edge maps were the best configuration for structural controls, and the edit strength of 1.5 and inference of 20 to 30, a range of 20 to 30 were the good set of configurations to generate images that look store-like for store-like layouts. And we can see a sample of the generations here, a random sample again, some of the good and the noisy generations that we categorize from these outputs, and see the good generations on the left. We could see that how the structure is, overall structure is pretty much done, but you can also see some of these places are enclosed. This is probably what was learned from the source dataset. So as a part of the source dataset, and that should be a bit more diversified. So maybe to fine tuning how the source dataset looks like and structure that might enhance it a bit better, but this is still good enough for segmenting task, which is what the part of the store layout optimization usually uses. So for the identifying segments, it's picking it up pretty well. And you can also see the second image is more generic towards how the outdoor and the indoor both map down. You can see some fields that are colored also, because that is learned from the images, and that is also good generation from this DoGE framework. On the right side, as you can see, there are some noisy generations. We can see that the image is not clear enough. It's still unrefined. So these are some bad examples that are filtered out. So we'll have to manually filter them out. But there's still good generations around there's a 50-50 generation based on the required task of, if it's a segmentation task, again, you can see on the left, there's some good images. On the right, there's much more diverse. So we also saw some other generations that bring in a bit more different diverse data sets. So these are the generations of how the image look like using the DoGE framework. The limitations of this project. So one of the problems that we notice is that the target datasets contain highly annotated images, because these are mostly formed from Google, and they were highly annotated. You would see images being embedded, like labels being embedded on top of the images, and that caused a noise to be introduced into the generations. So that is one of the problems that we noticed. And blurriness and noise in some outputs. We can also see that some of the outputs generated those noisy outputs, and this is also contributing a factor that is contributed to the labels and the marking, the arrows marking to these specific parts of this map. So those are some two problems that were identified. And also computational intensivity for high inference steps. So if you did notice that the best configurations for inference steps are 20 to 30, and whenever there's a higher inference step used, the computational intensity increases, and the time taken for generations also increases as a result. So that is some of the limitations of this project and the DoGE framework used in this specific domain. So as a part of the future work, we experimented on canny maps and head maps for as a part of this research, but we can also extend semantic segment mappings, which is basically identifying segments within the map within the images, some advanced guidance techniques. So this can better structure the output. So this will reduce the noise a bit more. And also you can use graph neural networks to also identify components of the image and then be able to find out how to generate those specific components better. So those are some advanced techniques for guidance that can be used to ensure that the output generated is better guided. And for efficiency optimization, the embeddings that are being used can be used. A lightweight embedding method can be used for the of optimizing the efficiency. Optimizing the efficiency. So optimizing the generation or the embedding extraction. So this is basically clip or unclip can be removed and used with other semantic models that are used for text to image or image to text, so that they can be used for embeddings and generation from them. So the unclip, again, the stable diffusion model for here that is used is unclipped. So again, swapping out them with different efficient optimizations can make the process much more smooth and less computationally expensive. And another future enhances maybe checking out specific applications for supermarkets, warehouses, boutiques, sub-classifying the domains that are outputted, and then checking out how they perform well under those circumstances, and are they able to specialize in these aspects. So those are some of the other future work that can be done. Overall conclusion of this research, it is brought to light that DoGE framework is really effective in this situation because it is generating images that is very effectively segmented and usable in the store layouts. The reason why I wanted to test out the store layouts was also with the specific DoGE frameworks is that while it also addresses the other problem and it solves it pretty well, another is that this is not having explicit features, but it's much more nuanced about how the store layouts look, more rigid generations. While generations usually have problems with being able to affirm to that rigidity. So that's one of the problems that I felt generative models might face. But DoGE was doing it pretty well because of their structural component, that the ControlNet that introduces the structural guidance, and that is what makes it much more effective to use in certain situations where the segments are necessary. So I believe that that's where the DoGE framework was effectively used. So that is a conclusion that we can come to. And also, we also understood the potential retail operational optimizations that can be done with the generated images, because now we have store layouts that are very well segmented and can be components, are segmented as components. And these can be used to identify shelving aisle design or customer flow prediction. And all this analysis can be done on these images. So that has been enhanced as a part of this. So the data set can be used for such situations. So that's a good outcome of, that's a conclusion from this research. And also the synthetic data generated by DoGE also improves AI world and real world applications, which is what I was referring to as a part of the previous project. This process would make it more available, make it such that there's more available data to experiment and train different models as a subsequent step to optimize the navigations. So that concludes my research project on this submission. And if you have any questions, you can please drop it down as comments, or you can drop it down as questions in the portal.